vertical line test. When we're given graphs of functions, and let's distinguish the graphs. These are our given graphs. Let's move these. We want to know if they're vertical line tests, which we said every x has exactly one y to go with it. Basically, when you do a vertical line test, if I was to draw a vertical line, it could only touch the blue graph in one place. Is that the case? Yes, it only touches it one time, so we would say, is this a function? Yes. What about the second one over here? If I drew a vertical line anywhere, let's just say I picked here, what it touches the function two times. That means for this value of x, they have two y values that correspond with it, so this fails to be a function. How do you feel about the next one? Function or not a function? Yes, it's a function, because if I draw a vertical line here, it touches it one time. Let's just say I randomly said I want to draw a vertical line here, it still only touches one time. Let me throw this at you. If I have a function that is a circle, a relation that's a circle, is that a function, yes or no? No. No, it fails the vertical line test. So a circle would not be a function either. And those are our favorite because they're the easiest ones to work with. Next, we're going to use the graph to determine the following. The function's domain. What did we say the domain was? The x values. Good. To describe the domain, we can use interval notation. Let me show you and remind you of interval notation. And let's make sure that these have arrows on each end. So all of my x values for their domain, you want to know the leftmost to the rightmost. So what would you say our interval is? Negative infinity to positive infinity. So interval notation is simply negative infinity to positive. We want to do leftmost to rightmost. If it was set notation, let's just recall some notation. I would say the domain is going to be x such that x is any real number. I think that's how one of the textbook does it. You can also do x as an element of the real numbers with like the real number like this. There's tons of ways to do it, but basically that's a similar format for that. The function's range, remind me what range is. Range is going to be all the y values, and don't forget ranges needs to be from bottom to top. Bottom to top. So we would say the bottommost value, let me use a different color. What's the bottommost y value we hit in our function? -5, bracket or a parenthesis? Bracket. You want to use a bracket there, good, because we want to include it in the set. Parenthesis would mean it's not included. So bracket 5, and then topmost is infinity because it is arrows. Okay, the next thing we're going to recall is our x-intercepts. And remember that x-intercepts are where our graph crosses the x-axis. So it looks like, because we're calling this is our x-axis, I'm reminding you that this one is the y-axis. Our graph crosses here and here, so we would say our x-intercepts are the ordered pair -5, 0, and the ordered pair 5, 0. Now, depending how you're asked that question, sometimes in my math lab you might say just -5, comma, +5. But if they ask it as an ordered pair and it's driving you crazy because it keeps marking you wrong, then that's the ordered pair notation of the same thing. It usually will tell you in parentheses, it'll be precise underneath. The y-intercepts is going to be where it crosses the y-axis, which is going to be, what do you think? The order, and let's do it in the ordered pair. So 0, -5. And the last thing we're going to do on this is the function value. So evaluate f at -3. We could do that we did that algebraically on the last video, but this time we have a graph. And maybe I'm going to try to erase this stuff so we can see a little better. When the x value is -3, so if I were to move over to -3 and then go down to my function, what is the y value at that point? So what I'm looking for is go into x is -3, I arrow down to my function, and then come over to say the y value is -2. Good. Okay, moving on. State the intervals on which the given function is increasing, decreasing, and constant. Now, we just now talked about domain and range, and that incorporates using brackets and parentheses. But when we're expressing increasing, decreasing, and constant, it's going to be using all parentheses. We're just describing where that actually occurs on the function. So increasing, we want to liken that with going up, or it's increasing. So as we move across our page left to right, here to here is increasing. So we name that according to the x values. So we would say it's increasing at the x value of what? -2, and then it stops at what? -1. Good. That's our first part. This next part, from here to here, is not increasing. What about from here to here? Decreasing because it's going down. What about the next little segment? Increasing. So this one's increasing as well. So I need to describe the x values for that portion of our graph. So that would be increasing from 3 to 5. Okay, good. The function is decreasing, so now we want to know when we move left to right, when is it going down? So I come here and I can see when I move across my page, left to right, it's going down. So I want to describe that using the x values. It's going to be the interval, looks like 1 to 3. And constant. It is constant on -1 to +1. Use the graph to determine where f has a relative maximum. So we want to think it has a maximum here. So the maximum is, and basically it's going to be stated like this: 1, the maximum of 1, and it occurs at x equals 0. This is the formatting of how you would notate that in your homework. You would say the maximum occurs at 1. The maximum is 1, and it occurs at x equals 0. And then the minimum, so next we're looking for a minimum. So the minimum is what? -3. Good. And it occurs at x equals 2. Okay, so we have definitions of even and odd. An even function, basically when you are given a function and you evaluate it at -x, you should get the same thing that you started with. And the function f is odd if when you evaluate your function at -x, you get exactly the opposite of the original function. And we're going to practice in these next three problems. We're going to evaluate all our functions at f of -x, and then afterwards we'll evaluate what the situation and determine if they're even or odd, or possibly neither. So I'm going to pause it and we're going to do all of our work, and then we'll go back and make our conclusions. Okay, now that we've evaluated each one, we want to compare our result to the original. And this one is exactly the same, x squared plus 6. So we would say if we evaluate f of -x and you get the original function, we know that it is even. So this one is an even function. In B, g of x, when we evaluate it, we get the exact opposite. You get negative 7x to the cubed when it was x cubed when it was the original, and it's positive x when this one's negative x. So term for term for term, it's the exact opposite of what was the original. So this one is going to be an odd. And we look at the last one. The first term is opposite in sign, negative x to the fifth. This was positive, and then but this one's the same. So if it's not exactly the same nor exactly opposite, then we say neither. So this one's neither. Okay, the graphs of even and odd functions we'll see below. This has y-axis symmetry and would look something like this. So an even function, if you folded the paper in half right here, it would match up. Odd function has origin symmetry, and you can see here, and it's completely opposite. So if the order pair is 1, 2 over here, it's the exact opposite over here, which is negative 1, negative 2. So you can kind of get a visual to also go with the algebraic notation of even and odd for your functions.